So we are on page 111. We're going to talk about the normal distribution. Now you need to, I did the finger quote thing around the word normal. You need to throw out your idea of what normal means, because in this sense, the word normal is not what it normally means. Oh, yeah. A little math humor there for you. In tutorial 3.1, you constructed probability distributions for discrete data. In this tutorial, you will explore distributions for continuous data. And all the real difference means is, if it's continuous, that means there's things in between. And I really would not worry too much about what the difference is. Okay? An inspector for a potato chip manufacturer measured the masses of 500 bags of potato chips to the nearest gram. That sounds like a nice job, eh? You take 500 bags and weigh them.
110, right?
The results are displayed in the two graphs below. The frequency graph shows the number of bags for each mass. The probability graph shows the probability that a randomly selected bag from the 500 bags has each mass. The probabilities for this graph are calculated by dividing each frequency in the frequency graph by 500. So now, if you look at these two pictures that you have on that handout, would you say that they're almost identical? In fact, what difference can you find between them? Is there any difference at all? No. The numbers on the side, you're absolutely right. That's the only difference. The picture itself is exactly the same. So this is simply the frequency graph. This is all 500 bags of chips, right? And they measured the weight of them. You'll notice that the majority of the bags are sort of somewhere in the middle here, right? Looks like about 84 grams or so, something like that. Some bags were a little bit more, all the way up to, looks like 89. And some bags of chips were all the way down to about 72 or something like that. Okay? Although not too many like that. This type of distribution is what we call normal. Now, the one on the right here, this is the probability graph. This just means that if I went into that mass of 500 bags, if I went into all those bags, pulled one bag out, the chance that it would be 80 grams would be about almost 0.14. About a 14% chance. How come? Because the most of them is that size. So these basically show the same thing. This is the graph for 500 bags. This is the graph for chance of one bag being a certain mass. But they sort of kind of mean the same thing. Okay, so that's all that those two things are. And really not something you need to sort of know specifically, just sort of some background information. Flip the page over. The company makes thousands of bags of potato chips. They can't just make 500. If we measure the mass of each bag to the nearest milligram and create a probability graph like the one on page 111, the midpoints of the tops of the bars would form a curve similar to the one in the graph below. In other words, if I took a point in the middle of the bar, like so, and then connected them, it would look exactly like this. And this, my friends, is called the normal curve. It's the normal, sometimes referred to as the bell curve. Why is it called the bell curve? It looks like a bell. Okay? And quite often people talk about things being normally distributed. Just about everything you can think of is normally distributed. Okay? If we were to measure your shoe size in here, although there's not that many of us, you would find it normal curve. Most people would have an average size foot. There'd be some of us with a really big foot and some of us with a really small foot. If we were to measure height, same thing. Intelligence, same thing. Student marks, probably the same thing. Some of us would be really smart. Most of us would be average. Some people would be below. No names associated with any of them, right? But most things are normally distributed. Okay? A lot of things. Okay? So how does this thing work? Okay? Okay, Rowan, we don't need to get into all that. Or, sorry, Steve. By the way, I would encourage you to make little notes right on that handout. And if you haven't done so already. Okay, now this picture right here is kind of important. Let me just make it a bit bigger so we can see things a little bit better here. Okay, so it says, I'm just going to read above it. The bell-shaped curve is a graph of a normal distribution. Many characteristics of manufactured products, such as volume, mass, and length, have probability graphs that closely approximate a normal distribution. Human characteristics such as height, mass, and intelligence have probability graphs that closely approximate a normal distribution. Every normal distribution is identified by its mean and standard deviation. Examine the normal distributions in the diagram below. So first of all, let's look at the two that have the same shape. And I'm just going to color over it, this one. I'll make that one blue, and I will make this one red. Would you say that the shape of those is the same?
Yes.
They are the same, okay? So, but they are in a different location. So you'll notice here, different locations, same shape. The mu values are different. The 25 is in the middle here. Here's the 100. But what about the standard deviation? It's the same, right? So the shape is determined by the standard deviation. And if I'm to look over here now at these ones, and if we just talk about this one being the black one right here, this one is in the same location, right? What do you notice about the means? Same mean, but different standard deviation. Okay? So any distribution that is normal has a specific mean and standard deviation that determines where it is on a graph and its shape. And you should know the difference, what the location and the shape are the mean and the standard deviation. Okay, now at the bottom there is a purple box that's kind of important. Do you guys have the purple box anywhere? You do not. Okay, so we should probably, let's put that purple box into regular guy talk. Can we do that? Properties of a normal distribution. Every normal distribution has a mean and standard deviation. Well, that's pretty straightforward. All normal distributions have a mean and standard deviation. All normal distributions have a mean and a standard deviation. Uh-huh. I suppose. A mean and a standard deviation. The graph is symmetrical about the mean. It is, how about we say, same on both sides of the mean, right? The left side looks the same as the right side. It's symmetrical. Go ahead, Luke.
I don't mean to insult you,
but I have really bad handwriting? Yeah. No.
Can you read the top one?
Sure. All normal distributions have a mean. You know what? How about we do this?
Convert to text. Type it. Bam. Bam.
Would you look at that?
Yes. You should do the other one.
See, the computer understands me, Luke.
Yeah, special program.
All right, the third one is almost all of the data lie within 3 standard deviations of the mean. I'm going to replace almost all with 99.7% of data is within 3 standard deviations of the mean. Let's see how it does with that.
What does that mean?
I'll explain that, yeah. I know that's a little... Look at that. That is just so cool. So when I say within 3 standard deviations of the mean, you're going to see what that means when we get to the next chart there. On page 113. So just sort of hold that back in your mind. The fourth one is that the curve approaches the x-axis, but does not touch. I guess I could say it. The curve approaches the x-axis, but does not touch it. Oh, that sucks. Why did it do that? What that means, yeah, it does look like a ransom note, doesn't it? What it means here is on this thing here, the blue line comes down to the x-axis but doesn't actually touch it, is what it means. Okay, and I'm not really going to get into what that really means. And I'm going to say the total area under the curve equals 1. The total area under the curve equals 1. Okay, so that's sort of the basic properties. Although those are sort of basic definitions that really probably don't have a lot of use to you. However, the next one is very useful. Okay, do you guys have this chart on the next page? Okay, this chart is super important for you. Okay, super important. The normal distribution is useful because certain percents of data values fall within specific distances from the mean. Some examples of these relationships form the 68, 95, 99% rule. That is a rule you need to know, Stephen. The 65, 95, 99 rule. And what that says is 68, 95, 99. About 68% of the data are within one standard deviation of the mean. You'll notice on your chart, you do not have anything on the bottom here. See that? I would like you to write in right here. I'd like you to put mu right there at the center. And this is what we call mu plus 1 standard deviation. This is mu minus 1 standard deviation. Okay, and I'm going to give you an example right away that goes with that chart that's not in the book. Okay, mu plus 1 sigma, 1 standard deviation. This is mu minus 1 standard deviation. This next one here is mu plus 2 sigmas. This one is mu minus 2 sigmas. And keep going, mu plus 3, mu minus 3. Generally, you can stop after 3. If something is outside plus or minus 3 standard deviations, it's considered abnormal. Okay, so what does this mean? Let's say, and if you've got room here, let's just say here we've got a test, and let's say that the average on this test was equal to 60. Okay, let's say we wrote a test, the average was 60. And let's just say for easy figuring, the standard deviation was 10. Remember, the standard deviation being 10 tells us how spread out the numbers are. Some people got way more than 60. Unfortunately, some people got much less than 60.
Okay, so if you're saying the mean is 10, what does that mean?
I'm going to tell you right away. That's a good question. So what that would mean is, in our example here, the mu value is 60, right? So I would put my 60 in the middle. The average for the class was 60. If I were to add 1 standard deviation, then I would get to 60 plus 10 would be 70.
Oh,
Mu minus sigma would be 50. So what this means is 68%, obviously we're a small class. If this was a bigger class, the average in the class was 60. 68% of you, a little over 2/3, would have got a mark between 50 and 70. 2/3 of the class is between 50 and 70. Now, what happened to the other third? They're above 70 and below 50. Okay? So we'd go to 2 standard deviations. So it's 60 plus 2 tens is 80. 60 minus 2 tens is 40. So now we've got a wider range. So we've got more people. Now we've got 95%. Almost everybody in the class is between 40 and 80. There are a few people, there's 5% that are either above 80 or, unfortunately, below 40. Okay, to include them, we'd have to go wider. We got mu plus 3. Now we're at 90 here. Here we're at 30. 99.7.
really?
Almost 100% are within 3, so almost 99.7 are between 30% and 90 on the test. Sorry, 30 and 90 on the test. Does that make sense? Yeah? Now, again, that's just an example, right? It's good, Dylan? Makes sense with that example? Okay. So let's go now to... Now, in a very timely... It's always good that we do this in the second semester because a bag of Cadbury mini eggs. Everyone loves mini eggs, right? No? A bag of Cadbury mini eggs has a label that reads 43 grams. Every hour, 10 bags are taken with the production line and weighed. Here are some of the results. So number 1 says, enter the data into list L1 of your calculator and calculate the mean and standard deviation. Round your answers to 2 decimal places. So I need you to put all those data. They're in 3 rows. and I want you to put all of them into one list and find the mean and standard deviation, and I'll meet you on the other side. So we've got our numbers in. Now we're going to go stat, calculate, one variable stats, right you are, L1, and we find out that the mean and standard deviation is 43.86 and 0.76. So I'm just going to cut and paste that over.
And I've got one.
Okay, if you missed one, that's fine. Okay, but that's how you would do it, right? All right, we got the data in there. Now, so what I need you to do, now, when I made up my example, I used nice easy numbers like 60 and 10, right? It's not going to be the case. So the average is 43.86. So let's put 43.86 right there.
Between the 234.
Right in the middle. Now, right sort of at a bit of an angle, because this next one is going to be 43.86. Remember, it's plus 1 standard deviation. So plus the standard deviation of 0.76, which equals 44.62.
Yeah,
44.62.
see, I thought it was like that too, but then how come on here it says between 25 and 50 is standard deviation?
Because you're still on page 1 of that chart.
Yeah, we're saying concept there.
Yeah, but different numbers, different question. So same idea, but okay. Now I've got to go on the left-hand side here. I'm going to write exactly the same thing, 43.86, but now I'm going to subtract 1 standard deviation. And that gives me 43.10. Okay? Do the same thing, both sides. So that's the 1 standard deviation. Now you're going to do it. I'm going to do it in blue just so you guys can see the difference.
What is the subtract one equal to?
43.10. The next one is 43.86 plus. Now remember here you got to go 2 standard deviations. So you got to go 2 times that 0.76, giving us 45.38. 45.38. Down here, 43.86. Now it's subtract 2 standard deviations. Well, yeah, I mean, and you're not going to have to do this every time, you guys. This is just purely for illustrative purposes, just so you get what's going on. 42.34. Okay, and I'll just quickly jot these in here. They're actually, the answers are on the next page, if you haven't figured that out yet. I wanted to show you where they came from. 46.14. And this one here, I'll just give you 41.58. So what is this good for? Well, you can use this to predict how many bags of mini eggs are going to be within a certain range. Now, why would anybody care about this? Well, if it says on the bag of mini eggs that the mass of it is 44 grams, but 90% of yours are 64 grams, you got a problem. You're charging people for 45 grams, but you're actually giving them far more, right? So quality control.
Would little kids have to care?
Little kids won't.
But people that do drugs might. It's a lot of time.
Well, yeah, if it's supposed to be 200 milligrams of ibuprofen and you're getting 400, that's a problem. Or something else.
If you paid for 200, you got 400. Would you have to complain?
Well, no, but the company would be losing money pretty quick, wouldn't they? And their shareholders wouldn't be.
Yeah, it's either.
Yeah. So they want to be consistent. Consistency is the key, kind of thing. Okay. So.
Yeah, I was trying to.
Huh?
You can share.
Doesn't have to be federal company. Huh? Well, pharmaceuticals like Bayer and Procter & Gamble and all the big pharmacy companies, yeah.
Johnson and Johnson.
Okay, so the question said, question number 2, roll it on page 113. If the distribution is normal, find the proportion of bags of mini eggs with mass that is less than 42.34. What percent is less than 42.34? Well, here's 42.34. What percent is less than to the left of it? Now on your charts, you should have, you guys have these ones as well?
2.45.
Okay, exactly. How did we come up with that number? Let me just make some room here. Okay, so this is 2A right here. So what percent is less than 42.34? So you sort of shade in this value right here. Okay, now where do these numbers come from up top here? I didn't really explain that very well. Let's go back to this one here. Where do these two 34s come from? What's the rule? Plus or minus? 68, 95, 99, right? Stephen, what's half of 68? Stephen,
Yeah, I know, I'm listening.
what's half? 34. So 34 is plus or minus 1. 34 on both sides. Where the heck does 13.5 come from? Well, remember it was 95, right? 95 minus 68 is 27%. So when you go wider, you go to 2 standard deviations, you get 27%. What's half of 27? 13.5, right? Now we're at 95%. Outside 95% is another 5%. It's this 2.35, and then 0.15 is actually above. So that's where those numbers come from up top. These numbers actually rolling across the top are constant. They're always the same. These two add up to 68%. These four add up to 95%. And I went too far on this one here. These ones here add up to 99.7%. Okay? So that's where these numbers come from up here. If you add those all up, you get 99.7. They're always going to be the same.
Will it always be marked on the test, or will it be marked for us to write?
Actually, you will never use them. I'm just giving you the most basic kind of question. Tomorrow we're going to, because you're going to ask me a question right away. So hold on to that thought. Hold on to that thought. So the question really is on page 113, and I'm almost done, you guys. Hang on here. I got a couple more examples to show you, and then I'm done. What percent is less than 42.34? So 42.34 is right there. What percent is less? So I go to the left, I shade in, and I add those two numbers. So I take 0.15 and 2.35 and get 2.5% of bags are less than 42.34. Okay? The question asks what percent is less than 42.34? I look at the chart, I can see that it's 2.5%. It is, it's pretty easy, really. It also means the flip side is, Rowan, if you randomly pick one bag, what would be the chance that it is less than 42.34? 2.5%. 2.5% of all bags are less than. One bag has a 2.5% chance of being less than. Okay? So the next question is to be greater than 44.62. Greater, let's make some more room here. Greater than 44.62. How do you do that? You find 44.62 on the bottom. Because it's greater, which way do I go, Lacey? To the right, exactly. Greater means to the right. Shade those in, and then simply add those numbers up. That's all you do. 13.5 plus 2.35 plus 0.15. That's all you do. 16% is the number. 16% of all bags are greater than 44.62 grams. The last one, oh yeah, that's right. I guess it is shaded here, right? Yeah. Okay, well, between 43.1 grams and 45.38 grams, so find 43.1 and 45.38, shade it in, add those up. 34 and 34, and 13.5 is a total of 81.5%.
Yes, please.
81.5% of all bags are actually between, right? Are somewhere between 43.1 and 45.38 grams. Now, if you haven't thought of it already, you're probably going to say, well, Mr. Bennett, what if it's not 43.1 and 45.38? What if I want to know 43 and 46? How the heck am I going to do that? Because 43 is where? 43 is like a little bit to the left, and 46 is a little bit to the right. How the heck am I going to do those? And the answer's tomorrow. Okay? And in fact, when I show you how to do it tomorrow, you're not going to have to do it by the chart today. Once you see how to do it on the calculator, it's fairly simple. But this gives you an idea of what's actually going on. Okay? On a scale of 1 to 5, how much do you get?
2.5.
Hold up your hand. You know, on a scale of 1 to 5. 3? 4? Rowan?
Sitting at 3.
Sitting at a 3, okay.
2.5. He was drawn thing.
Yeah?
Outdrawn.
Luke, how did I do? Give me a score. How did I do in the explanation? 1 to 5. How much do you get?
5.
Give me a 2, wow.
Oh, Scheller, he's smart.
Sheller's give me a 5, okay. Dylan, how did I do?
3.5.
3.5?
5.
Okay. Here's what I recommend you do. Okay. On page 116, for sure do number 2. If you can do number 2, you're good. If you can do number 2 and get everything right, then you're good. Okay? You should probably do a couple more though. I'm going to say 2, 3. I'm going to say 2, 3, and 6. Okay, 2 is a bit long. You know what? I'll be generous. In part 2, only do, I'll say 1, 3, and 5. Fair enough. But I recommend you do them, Ron.
I will.
I know.